Hello everyone, and welcome to this video where I'll be taking you through a question related to the objective. Write the parametric equations for a line segment given an orientation. So in this video, I'm going to be working on just one question from Knewton.com's Knewton Alta homework system related to this particular objective, and hopefully watching me do it here will help you out, if you come across a problem in that same objective when you're working on it on your own. And as with every problem, I would also say, when I start working on the problem, before I even get into it, I would suggest you pause the video, try to work out the problem yourself, and then come back and watch me go through it and compare your work to mine, see how you're catching on. All right, so here it is, the one question I wanted to go through. All other questions for this particular objective are similar. All right, there's the answers, sorry. But we're given the question, a particle moves in a straight line from point A with coordinates -10, 6, this is on the xy plane, of course, to the point B with coordinates 7, 8. And it does this in 48 hours at a constant rate. Okay, so that's an important notion there. This is a constant speed at a constant rate that this particle is moving at. The coordinates are given in centimeters with respect to the standard xy coordinate plane, and we're asked to find the parametric equations with respect to time t in hours for the motion of the particle. Okay, so time t will be representing time in hours, and at time 0 hours, at t equals 0, the particle will be at the location -10, 6, and then t is an hour, so at t equals 48, we would like the particle to end at, be at the location 7, 8. Okay. So there are multiple ways to parameterize any curve. Right? You may have seen this in your reading or studying before on parametric equations. So one way to go about this would be to find the distance, the length of the segment being drawn. So you could use distance formula. This is more complicated than what I'm going to be doing in a second. But you could parameterize this by, taking the length of this segment and then, you went from here to here, you went that, whatever the length is, number of centimeters in 48 hours. Your constant speed would be that many centimeters per hour. I divide the length of the thing by 48, and then, set up a parameterization so that when t equals 0, you're here, and t equals 48, you're over here, moving along that segment. And, the distance formula is not really super necessary here, as I'll show you. Is when you take a distance, when you take a length of a segment, you can, take a distance on the XY plane and the speed at which you're traveling, and you can always break things up into horizontal and vertical components. And those components should, also be changing at a constant rate, at the length of the segments moving, if the particle's moving at a constant speed as well. So I'm going to do that. All right, so I'm going to draw this out. So I'm just going to do a rough sketch here. I'll go to that desmos.com site in a minute. We'll get a better looking picture than what I'm drawing here, but here's the XY plane. The particle is starting at the negative, these are in centimeters, these marks are in centimeters, they said. So point A, right, the initial position of the particle is at -10 centimeters, 10 centimeters left of the origin, and then +6 centimeters above the origin. So this is point A right here, right? Negative 10 comma 6. And then we're moving from this point to point B, which was at the point 7, right? So positive 7 centimeter mark on the x-coordinate, x-axis, 8. All right, I'll put 8 up here above 6. Positive 8 centimeter mark on the y-axis. So here's point B, and then this is the motion. You know, the objective had the words given orientation. Here's the orientation of this curve, right? We're moving on a segment, tracing out this segment, moving in that direction from point A to point B at a constant speed. And this is in, 48 hours. So, and, T represented hours, right? So T, when I'm tracing this out, has to go from, 0, right? Because it's 0 at the 0 hour. So I'll put T equals 0. At the 0 hour, we're at point A. And then we need it to be so that at the 48th hour, right, when T equals 48, we're at point B and moving in that direction at a constant speed. All right. Well, instead of doing it on the diagonal on this segment here, right, like I mentioned earlier, you can always take a segment like a vector. We'll talk about vectors in other videos, and break it up into horizontal and vertical components when you're on the XY plane. So I'm going to look at the horizontal motion, which again, if things are moving at constant speed, the horizontal component should change at a constant speed, and the vertical component should also change at a constant speed, a constant rate. So to get from here to here along this segment, it's like going right this far and up that far and both of them moving at a constant rate. So the x component, the horizontal component, let's take a look at that first. So the change in x, so again, moving, we have a constant rate of motion, constant speed, constant rate of motion here. When I move from point A to point B, x, increased by 17 centimeters, right? It went from negative 10 to positive 7 over that 48 hours, right? So the constant rate of speed is, 17 48ths, which really doesn't reduce centimeters per hour. And that's how fast the x coordinate is moving. And then I'd like to then set it up so that, when t equal, so we're going to have x, I want to set up a parametric equation here. I want the x coordinate to depend on t so that, at t equals 0, we're at negative 10, and at t equals 48, we're at 7. Right? X to be negative 10 when t equals 0, and x to be 7 when t equals 48. And that's a very simple linear equation, right? When we're moving at constant speeds, you should be thinking linear equations. So I'm going to have this in like slope-intercept form here. 17/48 is like the slope of not the line, that's not the slope of this line, but the rate at which the x coordinate is changing is like the slope, right? A rate of change times t. And very simple, if I want x to be negative 10 when t is 0, well, when t is 0, this term is gone, and then just throw a minus 10 on this. And that should be good enough for the parameterization of the x coordinates. And when t is 48, see how 48s would cancel here? If t were 48 and you'd have 17 minus 10, the x coordinate would be 7. There. This is perfect for the parameterization of the x coordinates if things are moving at a constant speed. And then very similarly, in a very similar fashion, the y component, I'm going to do it the same way. Again, the y, everything, the particles moving at a constant speed, constant rate. So the y coordinate should also be changing at a constant rate or a constant speed. And let's see, if I move from here to here, the y coordinate went from 6 to 8 over that 48 hours. So that's an increase of 2 centimeters in the y direction over that 48 hours. Now 2 does go into 48 evenly. There, you can reduce this. 17/48 couldn't. So the speed, right, the rate at which the y coordinates are changing is 2 over 48 or 1/24 centimeters per hour. Right, once again, parametric equation then set up an equation to say what the y coordinate is for any value of t. I'm going to have, again, some linear expression here with a constant rate of change, right? Things with a constant rate of change are linear expressions. The 1/24 times t, right? Again, the rate is like the slope, even though I'm not talking about the slope of the segment, right? The rate of change of this y coordinate is what I'm talking about. So 1/24, the rate of change times t, and I would like, when t equals 0, the y coordinate to be 6. So just throw on a plus 6, right? When t equals 0, I'm at point A where the y coordinate is 6, so I'm just throwing on plus 6 there. And then you can see when t is 48, well, 48 divided by 24 is 2, and then you get 2 here, plus 6 is 8, right? And that's what I want when t equals 48. I want t equals 48. I want the y coordinate to be 8, which it is at point B at the end. So here they are, my parametric equations for this segment, where we're moving along the segment from point A to point B at a constant speed. X is 17/48 times my time minus 10, and y is 1/24 or 2/48 times my time plus 6. All right, so I'm going to double check this by going to Desmos, and I'll enter these as parametric equations, and put this, t ranges from 0 to 48 hours, t represented time in hours. So I'm going to put that as my range, and we'll see this exact same segment show up. All right, so back to the computer here. So here's desmos.com, right? Free online graphing calculator. Now, I've mentioned this in other videos. If you haven't seen it, you're seeing it now, though. If you want to enter parametric equations, right, you have to enter like an ordered pair. All right, so left parentheses, and then the x coordinate in terms of t was 17/48, right? That was the speed at which the x coordinates are changing, times t minus 10, right? That's what I had for the equation for the x coordinates in terms of time. And then comma, and then the y coordinate, y of t, I had as 1/24, right? That was the speed at which the y coordinate was changing, times t, and then plus 6. Right? So there was an equation representing the y coordinates. Now, when you do this, when you have this x coordinate, y coordinate in terms of t, it automatically sets up a range of t from 0 to 1. Now you can see here 0 to 1 is just simply 1 hour's worth of motion, right? T represented time in hours. Well, you can hopefully see that at t equals 0, I'm at the x is negative 10, y is 6. You can even put the point 10, 6, negative 10, 6 there, and then 1 hour later, I'm here. I want to change it to 0 to 48, right? Like we said, 0 to 48 hours. And you can see at the other end, we're at the point, 6, 7 for the x coordinate, and then 6, 7, 8, 8 for the y coordinate, right? It ends at the point 7, 8, as was mentioned in the problem. So here's the segment that gets traced out over that 48 hours, right there. Now, if you'd like to actually see the particle move, look at the motion of the particle, the motion of the point that traces out this curve. You can do this again, enter the parametric equations as some ordered pair, but instead of using t, right, because again, when you put in t, that's like standard, it'll have this range that you put in, from 0 to 48 like I did. Put in a different letter. Just replace t with some other letter, don't change anything else. So for the x coordinate, the speed was 17/48, centimeters per hour. And then instead of times t, I'll put times s. I like using s to replace t sometimes here. And then minus 10, right? So there was the same x coordinate equation with s replacing t, and then comma, y coordinate, 1/24 times t, but again, I'm using s, so 1/24 times s plus 6. And then you see after I do that, it's not putting in a range of s, it asks you to, add a slider. And I'll put a label on this so we can see what location we're at for any value of the parameter. Now this is automatically starting off at 1 for s. So remember, s is like t here, so this is where is the particle at after 1 hour? It's at this location. And I'll go to the slider here and change the ends from 0 to 48, just like earlier. And then the step size is, how much does the parameter increase or decrease as you move left to right. Now, if I want to go just every hour, we'll just have the step size be 1, see where the particle is at after each hour. So you see when s is 0, see I'm at the point negative 10, 6. 1 hour, 2 hours later, 3 hours later, 4 hours later, 5, 6, 7, 8, blah, 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 right, all the way up to 48. When I'm at the point 78, I'm at the point 78, 48 hours later, like they said in the problem. And you saw the motion happen, right? It started here, and then as time went by, the value of the parameter increased to 48 hours. You ended up there. Exactly as was described in the problem. You can also start at the beginning, and I'm going to, now you can't see it because of how much I'm zoomed in, but on the left side, there's this, little settings tab and a play button. You can you can do an animation where it, just goes forward, play once, play indefinitely, repeat in one direction, have it forward and backwards. I can just have it repeat in one direction here, and I'll slow it down a bit. And I'll even change the step size, make it a little smaller. So instead of the parameter increasing by an hour each time, I'll do it by 100th of an hour. I'll just have the step be 100th to make this nice and easy a smoother motion. And then I'll hit play, and you can see the motion of this particle as time goes by. 3 hours, 4 hours, 5 hours, 6 hours, 7 hours, 8 hours, 9 hours, 10 hours, 11 hours, 12 hours, and so on. And you can see this particle moving at a constant speed along this path from the point negative 10, 6 to the point 7, 8. And it eventually gets there, and I'll play the whole thing. Why not? And there it is, and then it starts again. That's the way it's set up. Beautiful. All right, so and then going back, and I'm in my instructor mode here, right? I'm not actually in an assignment, but so when you're in Desmos, or sorry, when you're in Knewton Alta working on a problem like this, they're just asking me for number 1, number 2, fill in those equations that we got, and these are the ones I showed you: 17/48 times t minus 10, 1/24 times t plus 6 for the y. Okay. And if you're working in Knewton Alta also, you get something right, you get something wrong, they'll have some sort of explanation afterwards. I would highly recommend reading through those as well. All right. So that's it for this. Hopefully watching me go through this one problem here will help you out with all the other problems that are very similar to this one, where you're parameterizing a segment, some particle motion along a segment at a constant rate. And thank you very much for watching.